I'm ready for ideas. This is from 10.1, so you know it's going to have to involve a system of equations. It involves a formula you guys should know from chemistry class maybe, or a physics class, involving distance, a rate, and a time. Do you know what formula I'm talking about?
Area equals, no. So this is something about love.
Love?
No, it's not volume.
Yeah, that's density.
Distance is equal to the rate traveled multiplied by the time traveled. Distance equals rate times time. It's going to involve some form of this. I'm open to suggestions. Story problems always seem easier when I come up with everything for you. It really does, huh? But then when it comes down to it, you guys have got to practice coming up with this stuff on your own. Okay. That's not a bad idea. What is it we're trying to find? The way that you solve a story problem is first identify what is being asked for. What are we even supposed to find? The speed of the boat and the speed of the river. So in that formula, is that D, is that R, or is that the T? That's the rate. Okay, but there is a slight problem. Well, that's one problem here we're going to have to deal with. This is a time in hours, that's a time in minutes, so that's not going to work. We have to have the same unit of measure. But the other problem, you guys, is this idea right here. How fast does a boat travel relative to the river? I need you to listen carefully. This is called point of reference. Okay? If you are an observer on the banks of the river, you need to imagine this, and you see this boat going by, okay? The speed of that boat is the speed relative to the banks of the river, okay? Now, is the boat really traveling the speed that the woman is rowing?
No.
What's the difference? Hey, BJ. Yeah, we're doing systems of equations.
We're doing an algebra 1.
Okay. Come on, let's get back to it. Come on. Zip it. Let's go, people. So the speed that that woman is traveling when you're observing her going by, what's causing her to move forward? The rowing, but also the stream. So, and then if she was going the other way, the speed that she's traveling is the speed that she's rowing, but she's fighting against the current. So is she traveling really as fast as she could be in still water? So we have to take into account this idea of point of reference. If I was floating along the river in some kind of an inflatable tube, and I saw the woman go by me rowing, would she be traveling as fast to me as if I were standing on the banks of the river? Does that make sense, what I'm asking?
No.
So if I observe the woman pass on the banks of the river, but then I hop in like some inner tube and I'm floating with the current, and then I see the same woman go by, would it appear that she's traveling slower or faster?
Faster.
If I'm on the banks, what would it appear?
Slower.
Well, if she's traveling, let's say she's rowing with the current. Okay, if she's rowing with the current, if I see her go by and I'm standing on the banks of the river, is she going faster? Or if I'm floating in the current with her and she goes by, is she going faster or slower? Isn't she going the same speed?
Yes.
But my point of reference has changed, right? So according to my point of reference, it appears she's going slower because I'm moving with the current, right? So what speed are they actually asking for here? The speed that she's traveling. At what point of reference? If I was an observer, where? If I was in the river watching her go by. So I'm just asking here to find her speed relative to the river. If she was rowing the boat in still water, like in a lake, without the assistance of a current, how fast would she be going? It's a little bit harder to find than just taking the distance and dividing it by the time, because that would give the rate of her plus the rate of the current. added together. We just want the rate of her rowing without the current.
So we have to find the rate.
And we have to find the rate of the current. So it's some form of this that we have to use, but it's not as simple as just taking how far she went and dividing it by how long it took her to get there.
Let's give up.
So once we identified what we need to find, what's the next step? We assign variables, right? How many things don't we know? We don't know 2 things. We don't know how fast the boat's traveling. We don't know how fast the current is either, so we need to assign 2 variables. So let's let x be the speed of the boat, and let's y be the speed of the current. Now I'm going to give you a hint and let you kind of think about this, because I don't want to do all this for you. It doesn't help you learn how to do this stuff. If you have 2 different variables to solve for, how many different equations do you need? You need 2 different equations. Okay? The hint I'm going to give you, split your paper up like this, make a big chart. You need to make a separate equation for the downstream trip. And then an upstream. And the formula you're going to use is distance equals rate times time for both of those. You're going to use a distance equals rate times time formula for the downstream, one for the upstream. So take a minute. Question for you. How
Is she traveling faster downstream or upstream? Why downstream? Okay, hold on. I want you to say it exactly how you just said it. Did you guys hear that? Her rate going downstream is the rate, it's the speed of the boat added to the speed of the current, right? That's why she's traveling faster going downstream. The speed of the boat added to the speed of the current is her rate going down. What's her rate going upstream? It's the speed of the boat, and then you take away the speed of the current, because isn't the current acting against her? Okay.
How far did she travel downstream? What was her distance?
4 miles.
4 miles.
4 miles both ways.
And it's the same going upstream. Her distance was 4 miles. Now, let's be really careful about how we describe her rate going downstream. The rate that she travels is the speed of the boat, x, but isn't it plus the speed of the current, y? And then how long did she travel? What was the time that she traveled?
0.75 hours.
0.75 hours. Okay? Isn't this a distance equals rate times time problem right there? Distance equals rate times time? Now we got to do something very similar for the upstream trip. She still traveled 4 miles, but this time what was her rate? It was the speed of the boat minus the speed of the current. And how long did she travel? Going upstream. 1.5 hours.
I see.
Okay, now we have to, we need to simplify this a little bit. We can't have the parentheses in here. You guys have a couple of options. You can either distribute the 0.75, or you can divide by 0.75 on both sides. It's up to you. If it were me, I'd rather divide by it so you don't end up with 0.75 as coefficients. But since we're using, or not using calculators, decimals aren't very easy to do by hand, so let me change that into a fraction. Instead of dividing by 3/4 on both sides, just multiply by 4/3. 3/4 times 4/3 are reciprocal, so they cancel each other out. On the left side, you have 16/3 equals x plus y. Now do the same thing on the right side, but again, decimals aren't very easy to do by hand. It'd be better to use fractions. What's 1.5 as a fraction? 3/2. So change 1.5 into 3/2, and now multiply it by the reciprocal on both sides. So you have 8/3 is equal to x minus y. We have equivalent forms of the same two equations here. We just have simplified a little bit so we don't have any parentheses. Now you got to think, why would this be in section 10.1? What did we just barely learn about in section 10.1? Systems of equations. What do we have here? We have a system of equations in terms of x and y. What we need to do is set this up. 16/3 equals x plus y, and 8/3 equals x minus y. Last time we learned about two methods, elimination or substitution. Either one would work here, but considering how this system is already set up, which one would make more sense? Probably elimination method, because the variables are lined up, and we already have opposite coefficients here. We have positive y and negative y. So if we added these two equations together, the y's would cancel. We end up with 2x is equal to what? 24/3, which is 8. Divide by 2, and x equals 4. But we have to be able to interpret this. Yeah, it's true that x equals 4, but what is x really? What does x represent? The speed of the boat in miles per hour. Now, this is the speed of the boat with the current, without the current, or what is this? This is the speed of the boat as if it were traveling in still water with no current helping it or taking away from it. This is how fast the boat would appear to be traveling if you were an observer in the water watching the boat go by. So, boat travels 4 miles per hour. Now we just got to find y, the speed of the current. How are we going to do that? To which one? Either one. Either one of these. Doesn't really matter. I'm gonna plug it in here for this one. So if x equals 4, then that becomes 16/3 is equal to 4 plus y. Oh man. Now we got to subtract 16/3 minus 4. 16/3 minus 4 is equal to y. What do we do?
You convert 4 into 12 over 3.
Okay, so this is 16/3 minus 12/3, and that's equal to y, which is equal to 4/3. Y is equal to 4/3. So the current moves at 4/3 miles per hour. There's one more type of application you got to be prepared for from 10.1. This is one that has a distance equals rate times time. Now your homework problems, it may be different. It may be a boat traveling against the wind or something else, but it's all just different ways of doing the exact same thing. You have to set up like an upstream and a downstream, or against the wind and with the wind type thing. The more you do with these, the more you figure out these are all almost the same problem. Whether it's a train, a boat, whatever it is, you set it up almost exactly the same way we did. You have a downstream and an upstream using the same formula, distance equals rate times time. One of the rates is x plus y, one of them is x minus y because they're traveling against either the current or you have a headwind. Does that make sense? So they try to mix it up with different types of things, cars, trains, it doesn't matter what it is. It's all pretty much the same thing. The other one sometimes aren't quite as easy to wrap your head around, but the more you do of them, the more you realize these are also the same mixture problems. These you just have to do enough of and get some practice with. You guys know what brine is? There's brine shrimp, but brine, it's like a saline solution type thing. It's got a lot of salt in it. There's 2 brine solutions. One contains 5% salt. How many, I spelled that wrong, sorry, 2 L's, milliliters of each solution should be used to obtain 1 liter of a solution that contains 14% salt. And this is not just some contrived problem that was made up to try to find a reason to do systems of equations. This kind of stuff actually happens. Biologists don't just have every single mixture they need on hand. They have 5%, 10%, 50%. They've got to mix them up in a way to end up with this odd percentage, 14% salt. They don't just have that lying around, but when needed, they have to mix a certain amount of chemicals in order to get that right concentration. So, we don't need to. We're too smart for that. And a calculator wouldn't really help. I mean, it would help with the computations, but not setting up the problem.
Probably have a science chemistry calculator.
No?
So there
You got your degree in this, you hope you
Well, they do it the same way we're about to. It's not that hard.
They want to figure this out. Yeah,
Come on, let's go.
I'm not going to be a scientist.
Why would this be in section 10.1? What do you think this is going to involve? Systems of equations, right? We need to identify what we don't know. And then assign variables. So what don't we know? What's the question here? Of what? How many solutions are there? 2. So, assign your variables. I want to see that you can assign variables without me telling you what they are. Write down something on there, what you think the variables are going to be, then we're going to talk about it. You don't have to use X and Y, it can be any letters. But I want to see everybody writing down what they think the variables are going to be.
I like that puzzle about you have a 5-gallon jug and a 3-gallon jug. You have to get 4 gallons.
In a way, yeah. Yeah, it kind of is, yeah.
You can't fill them up partway either. Well, you can't figure out.
At this step here, if you can't even identify and correctly label your variables, you have no hope really for solving the rest of your problem. You have to identify exactly what it is they're asking for. And this is what they really ought to be.
X should be the amount of the 5% solution. Y should be the amount of the 20% solution. And since we have two unknowns, we need to have two different equations to solve for them. So we need to come up with two different equations that relate X and Y. Both equations have to have both X and Y. It wouldn't make any sense to have one equation with just X and one equation with just Y. That wouldn't help at all. So you need to read through and try to decipher the information and try to relate the two variables to each other.
The information we need is in there. We just have to translate it from English phrases to mathematical phrases. First one is right here. How many milliliters should be obtained from mixing both solutions?
1,000 milliliters.
Okay, so how do we make this into an equation? Do you guys hear that? If X is the amount of the 5% solution and Y is the amount of the 20% solution, we know how much it's supposed to be together. It's supposed to be 1,000 milliliters. So X plus Y is equal to 1,000. Well, there's one equation.
The other one must equal 14%. So X plus Y equals 14. Or 0.5X plus Yeah.
Okay, that's more along the lines of what we've already done, just a raw amount of fluid. X plus Y equals 1,000. We need to do an equation that describes the concentrations of the fluid, not just the raw amount. So what's the concentration of the X fluid? What's the concentration of brine? Okay, so we can't use percents as numbers. 0.05x. What's the concentration of the Y solution? 0.2. And here's where most students make. Okay. Exactly. The mistake that's made is just to say 0.14. But it's a concentration of something. Here it's 0.05 of X. Here it's 0.2 of Y. This has to be 0.14 of something. How many milliliters, though? Which is 1,000. Does that make sense?
Most students, when learning this, will leave out that 1,000 and just have the 0.14 there, which is a mistake. It has to be a concentration of a fluid amount. Here, it's 0.05 of X milliliters. This is 0.2 of Y milliliters. This has to be 0.14 of 1,000 milliliters.
So we have the two equations. How do we solve it now? We could use either elimination method or substitution. It doesn't really. The thing that's concerning me a little bit, though, are these nasty decimals down here. 0.05, 0.2.
But if we do substitutions, then
That's what. How do you move decimals?
multiply
By.
100.
Well, multiplying it by 10 would move it one spot. Have faith. I'm going to multiply this bottom equation by 100. Why the number 100? It moves at the decimals how many? 2 spots to the right.
And then you have to do your top equation.
Nope. As soon as we finish this problem. So this bottom equation becomes what? 5x plus
20Y.
20y. Now be careful here. What is the 14 times 1,000, which is 14,000. We have not done anything to that top equation. It just stays x plus y equals 1,000. Since we did elimination on the last one, let's do substitution on this one. We need to solve the top equation for one of its variables. Doesn't matter which one. Okay, so you're going to subtract y then. So this top equation becomes x equals 1,000 minus y. You can take this 1,000 minus y and substitute it where? Into the x of the other problem right here. Okay, so that becomes 5 times 1,000 minus y plus 20y equals 14,000. So this is 5,000 minus 5y plus 20y equals 14,000. You guys solve it from there. You guys can finish this. Solve for y and solve for x. So y should be 9,000 over 15, which divides evenly. 600?
Yeah, because 15 goes in the 96 times.
Before you go back with solve, when we got to interpret this, 600 what? So should use 600 milliliters of the 20% solution. And we don't really need to go back and substitute into any more equations because we know that she needs to use 1,000 milliliters total.
600 milliliters are already used for the 20% solution. That leaves how many?
That's got to leave 400 because there's got to be 1,000 total. So should use 400 milliliters of the 5% solution. That's going to be 1,000 milliliters total, or 1 liter total. And if you combine 20% with 5%, you're going to end up with a mixture that's 14%. So those are the two types you need to be really ready for from 10.1. Some kind of a distance equals rate times time, and a mixture problem. All right, we need to move on.
10.2.
10.2.
How many sections are in chapter 10?
7.
That's a lot.
Yeah, chapter 10 is a big one.